4.5 billion years ago. In the early chaos of the solar system, two rocky planets formed from the same swirling cloud of gas and dust. They were almost identical in size, almost identical in mass, built from nearly the same materials. One of them became Earth, covered in oceans, filled with life. The other became Venus, the hottest planet in our solar system. A world so extreme, it can melt lead on its surface. Today, Venus orbits the Sun at an average distance of about 108 million kilometers. It completes one orbit in 225 Earth days, but strangely, it rotates extremely slowly. One full rotation takes 243 Earth days, meaning a single day on Venus is longer than its year. Even more unusual, it spins in the opposite direction compared to most planets. The Sun would rise in the west and set in the east. But rotation is not what made Venus a hell planet. The real difference lies in its atmosphere. Venus's atmosphere is incredibly thick and dense, made of about 96% carbon dioxide. The surface pressure is around 92 times greater than Earth's, similar to the pressure nearly 1 kilometer underwater on our planet. The surface temperature averages around 465 degrees Celsius. That temperature remains almost constant day and night because the atmosphere traps heat so efficiently. Thick clouds of sulfuric acid cover the entire planet, reflecting sunlight, but also sealing in heat below. However, scientists believe Venus may not have always been like this. Billions of years ago, the young sun was fainter than it is today. During that time, climate models suggest Venus might have been cool enough for liquid water to exist. Some simulations show that early Venus could have had shallow oceans, clouds, and possibly rainfall. If water was present, it would have acted as a stabilizing system for the planet's climate. On Earth, water plays a critical role in regulating temperature. Oceans absorb heat, clouds reflect sunlight, rain removes carbon dioxide from the atmosphere and locks it into rocks through chemical reactions. This process, known as the carbon cycle, acts like a planetary thermostat. If Venus once had oceans, it may have had a similar system in place. But Venus was slightly closer to the Sun than Earth. As the Sun slowly grew brighter over hundreds of millions of years, Venus began receiving more solar energy. At first, the warming may have been gradual. Oceans would have started evaporating slowly. As water evaporated, it turned into water vapor. And water vapor is a powerful greenhouse gas. This is where the runaway greenhouse effect begins. Greenhouse gases trap heat by absorbing infrared radiation emitted from a planet's surface. A small greenhouse effect is necessary for life. Without it, Earth would be frozen. But on Venus, as more water evaporated, more heat became trapped. As more heat was trapped, more water evaporated. This created a positive feedback loop. The warming fed itself. Eventually, Venus crossed a critical threshold. The oceans could no longer remain stable in liquid form. They began to boil away entirely. As the atmosphere filled with water vapor, ultraviolet radiation from the sun broke apart water molecules high in the atmosphere. Hydrogen, being very light, escaped into space. Oxygen reacted with surface rocks. Over time, Venus permanently lost its water. Without liquid water, the carbon cycle stopped functioning. Volcanoes continued releasing carbon dioxide into the atmosphere, but there were no oceans to absorb it. On Earth, carbon dioxide dissolves in rainwater, forms carbonic acid, and becomes locked into rocks and sediments. Venus had lost that mechanism. Carbon dioxide accumulated unchecked. As CO2 levels increased, the greenhouse effect intensified further. Surface temperatures continued rising until they stabilized at extreme levels. The planet entered a new climate state, one that has lasted for billions of years. This explains one of the most surprising facts about Venus. Venus is hotter than Mercury. Mercury is closer to the Sun, but Mercury has almost no atmosphere. When sunlight hits Mercury's surface, heat escapes quickly back into space. Venus, however, is wrapped in a thick blanket of carbon dioxide. Heat enters the atmosphere, but struggles to escape. The dense atmosphere traps thermal energy efficiently, keeping surface temperatures around 465 degrees Celsius across the entire planet. Even at night, Venus barely cools down. The surface conditions are extreme. The pressure is crushing. The sky is permanently covered in thick yellowish clouds of sulfuric acid. Winds in the upper atmosphere move at speeds over 300 kilometers per hour, circling the planet in just a few Earth days. Below those clouds, the surface is rocky, dry, and volcanically shaped. In the 1970s and 1980s, Soviet Venera spacecraft successfully landed on Venus. These missions provided the first images from the surface of another planet, but they survived only for a short time, some for less than an hour, the longest for about 2 hours, before being destroyed by heat and pressure. Venus is not just warm, it is permanently hostile. Scientists believe massive volcanic resurfacing events may have covered much of Venus's surface between 300 and 700 million years ago. Lava flows may have buried older terrain, releasing even more carbon dioxide into the atmosphere. Unlike Earth, Venus does not show clear evidence of plate tectonics. Without plate tectonics, there is no efficient recycling of carbon into the planet's interior. The climate remained locked in its runaway state. Today, the runaway greenhouse effect on Venus represents the most extreme example of climate change in our solar system. It shows how a planet with Earth-like beginnings can evolve into something completely different if certain thresholds are crossed. This raises an important question. Could Earth ever experience a runaway greenhouse effect? Current scientific understanding suggests Earth is not close to becoming like Venus. Our oceans are vast and stable. Our distance from the sun places us safely within the habitable zone. However, the physics of greenhouse gases is universal. Carbon dioxide traps heat. Water vapor amplifies warming. Feedback loops exist on Earth as well, though on a much smaller scale. Venus demonstrates what happens when those feedback loops spiral out of control without any mechanism to reverse them. Two planets, similar origins, different outcomes, a slightly closer orbit, a gradual increase in solar brightness, a chain reaction of evaporation and greenhouse amplification, the loss of oceans, the buildup of carbon dioxide, the permanent transformation into a high-temperature, high-pressure world. Venus did not become a hell planet overnight. It changed slowly, over hundreds of millions of years, through understandable physical processes. That is what makes its story powerful. Venus is not mysterious because it is alien. It is powerful because it follows the same laws of physics that govern Earth. By studying Venus, scientists gain insight into climate systems, atmospheric evolution, and planetary habitability across the universe. When we look at Venus, we are not just observing another planet. We are looking at a possible version of Earth. A reminder that small differences in distance, atmosphere, and feedback mechanisms can lead to dramatically different destinies. That is how Venus turned from a potentially Earth-like world into the hottest planet in our solar system. And that is why understanding the runaway greenhouse effect is not just about Venus. It is about understanding how fragile planetary balance can be. You're watching Infinite Cosmos.